An image is shown of a cluster of clear crystals, showing primarily cubic and some octahedral shapes. A large cubic crystal at the center of the photograph has a deep emerald green center with deep purple corners and a small royal blue region just right of center. A smaller cubic crystal to its left shows purple corners and edges with royal blue coloration toward the center. Similar coloration is seen in other crystals in the structure, though most of the smaller crystals are clear and colorless. Figure 15. 1. The mineral fluorite, Kf2, is formed when dissolved calcium and fluoride ions precipitate from groundwater within the Earth's crust. Note that pure fluorite is colorless, and that the color in this sample is due to the presence of other metal ions in the crystal. Chapter Outline 15. 1. Precipitation and dissolution 15. 2. Lewis acids and bases 15. 3. Coupled equilibria. The mineral fluorite, Kf2, figure 15. 1. Is commonly used as a semi-precious stone in many types of jewelry because of its striking appearance. Deposits of fluorite are formed through a process called hydrothermal precipitation, in which calcium and fluoride ions dissolved in groundwater combine to produce insoluble Kf2 in response to some change in solution conditions. For example, a decrease in temperature may trigger fluorite precipitation if its solubility is exceeded at the lower temperature. Because fluoride ion is a weak base, its solubility is also affected by solution pH, and so geologic or other processes that change groundwater pH will also affect the precipitation of fluorite. This chapter extends the equilibrium discussion of other chapters by addressing some additional reaction classes, including precipitation and systems involving coupled equilibrium reactions. Learning objectives. By the end of this section, you will be able to write chemical equations and equilibrium expressions representing solubility equilibria, carry out equilibrium computations involving solubility, equilibrium expressions, and solute concentrations. Solubility equilibria are established when the dissolution and precipitation of a solute species occur at equal rates. These equilibria underlie many natural and technological processes, ranging from tooth decay to water purification. An understanding of the factors affecting compound solubility is, therefore, essential to the effective management of these processes. This section applies previously introduced equilibrium concepts and tools to systems involving dissolution and precipitation. The solubility product. Recall from the chapter on solutions that the solubility of a substance can vary from essentially zero, insoluble or sparingly soluble, to infinity, miscible. A solute with finite solubility can yield a saturated solution when it is added to a solvent in an amount exceeding its solubility, resulting in a heterogeneous mixture of the saturated solution and the excess, undissolved solute. For example, a saturated solution of silver chloride is one in which the equilibrium shown below has been established. AgCl, letter 1D460, equals precipitation dissolution Ag plus letter 1D44, letter 1D45E, plus Cl minus letter 1D44, letter 1D45E in this solution. An excess of solid AgCl dissolves and dissociates to produce aqueous Ag plus and Cl. Ions at the same rate that these aqueous ions combine and precipitate to form solid AgCl, figure 15. 2. Because silver chloride is a sparingly soluble salt, the equilibrium concentration of its dissolved ions in the solution is relatively low. Two beakers are shown with a bidirectional arrow between them. Both beakers are just over half filled with a clear, colorless liquid. The beaker on the left shows a cubic structure composed of alternating green and slightly larger gray spheres. Evenly distributed in the region outside, 11 space-filling models are shown. These are each composed of a central red sphere with two smaller white spheres attached in a bent arrangement. In the beaker on the right, the green and gray spheres are no longer connected in a cubic structure. 9 green spheres, 10 gray spheres and 11 red and white molecules are evenly mixed and distributed throughout the liquid in the beaker. Figure 15. 2-silver chloride is a sparingly soluble ionic solid. When it is added to water, it dissolves slightly and produces a mixture consisting of a very dilute solution of Ag+ and Cl, ions in equilibrium with undissolved silver chloride. The equilibrium constant for solubility equilibria, such as this one, is called the solubility product constant, Ksp. In this case, AgCl, letter 1d460 Ag+, letter 1d44 letter 1d45e, plus Cl minus, letter 1d44 letter 1d45e, letter 1d43sp equals Ag plus letter 1d44 letter 1d45e, Cl minus, letter 1d44 letter 1d45e. Recall that only gases and solutes are represented in equilibrium constant expressions, so the Ksp does not include a term for the undissolved AgCl. A listing of solubility product constants for several sparingly soluble compounds is provided in Appendix J, Example 15. 1. Writing equations and solubility products, write the dissolution equation and the solubility product expression for each of the following slightly soluble ionic compounds. A. Agi, silver iodide, a solid with antiseptic properties. B. CaCO3, calcium carbonate, the active ingredient in many over-the-counter chewable antacids. C. Mg, O2, magnesium hydroxide, the active ingredient in milk of magnesia. D. Mg, NH4, PO4, magnesium ammonium phosphate, an essentially insoluble substance used in tests for magnesium. E. Ca5, PO430, the mineral apatite, a source of phosphate for fertilizer solution. A. Ag-I, letter 1d460 Ag plus letter 1d44 letter 1d45e plus. I minus letter 1d44 letter 1d45e. B. CaCO3 letter 1d460 Ca2 plus letter 1d44 letter 1d45e plus Co32 minus letter 1d44 letter 1d45e. C. MgO2 letter 1d460 Mg 2 plus letter 1d44 letter 1d45e plus 2 O minus letter 1d44 letter 1d. Check your learning, write the dissolution equation and the solubility product for each of the following slightly soluble compounds. A. BaSO4b, Ag2SO4c, Al O3d Pb, OCl. Answer. A. BaSO4, letter 1d460 Ba2 plus, letter 1d44 letter 1d45e, plus So42 minus, letter 1d44 letter 1d45e. B. Ag2. So4, letter 1d460 2 Ag plus, letter 1d44 letter 1d45e plus, So42 minus, letter 1d44 letter 1d45e. C. Al O3, letter 1d460 Al3 plus, letter 1d44 letter 1d45e, plus 3O minus, letter 1d44 letter 1d45e. DPbOCl, letter 1d460 Pb2 plus, letter 1d44 letter 1d45e plus O minus, letter 1d44 letter. Ag plus 2 So42 minus, Al3 plus O minus 3, Pb2 plus O minus Cl minus Ksp. In solubility, the Ksp of a slightly soluble ionic compound may be simply related to its measured solubility, provided the dissolution process involves only dissociation and solvation. For example, M letter 1d45d, X letter 1d45e, letter 1d460, letter 1d45d, MM plus, letter 1d44, letter 1d45e, plus letter 1d45e, XN minus, letter 1d44, letter 1d45e. For cases such as these, one may derive Ksp values from provided solubilities or vice versa. Calculations of this sort are most conveniently performed using a compound's molar solubility, measured as moles of dissolved solute per liter of saturated solution. Example 15. 2. Calculation of Ksp from equilibrium concentrations. Fluorite, Kf2, is a slightly soluble solid that dissolves according to the equation. Kf2, letter 1d460, Ka2 plus, letter 1d44, letter 1d45e, plus 2F minus, letter 1d44, letter 1d45e. The concentration of Ka2 plus in a saturated solution of Kf2 is 2. 15 times 10⁴ m. What is the solubility product of fluorite? Solution, According to the stoichiometry of the dissolution equation, the fluoride ion molarity of a Ca F2 solution is equal to twice its calcium ion molarity. F minus equals 2 mol F minus slash 1 mol Ca2 plus equals 2, 15 times 10 minus 4 letter 1 D440 equals 4. 30 times 10 minus 4 letter 1 D440. Substituting the ion concentrations into the Ksb expression gives letter 1 D43 ESB equals Ca 2 plus F minus 2 equals 2. 15 times 10 minus 4, 4. 30 times 10 minus 4 2 equals 3. 98 times 10 minus 11 check your learning in a saturated solution of MgO2. The concentration of Mg2 plus is 1. 31 times 10 4m. What is the solubility product for MgO2? MgO2, letter 1 D460, Mg2 plus, letter 1 D44E, letter 1 D45E, plus 2O minus, letter 1 D44E, letter 1 D45E. Answer 8. 99 times 10 12. Example 15. 3. Determination of molar solubility from Ksb. The Ksb of copper, I bromide Cu-Br, is 6 3 times 10 9. Calculate the molar solubility of copper bromide. Solution: the dissolution equation and solubility product expression are Cu-Br letter 1 D460, Cu plus letter 1 D44 letter 1 D45E, plus Br minus letter 1 D44 letter 1 D45E, letter 1 D43 ESB equals Cu plus Br minus. Following the ICE approach to this calculation yields the table. This table has 2 main columns and 4 rows. The first row for the first column does not have a heading and then has the following in the first column: initial concentration, M, change, M, and equilibrium concentration, M. The second column has the header of CUBR equilibrium arrow CU superscript positive sign plus BR superscript negative sign. Under the second column is a subgroup of 3 rows and 3 columns. The first column is blank. The second column has the following: 0, positive X, X. The third column has the following: 0, positive X, X. Substituting the equilibrium concentration terms into the solubility product expression and solving for X yields letter 1 D43 ESB equals Cu plus Br minus 6. 3 times 10 minus 9 equals letter 1 D465, letter 1 D465 equals letter 1 D465 2 letter 1 D465 equals 6. 3 times 10 minus 9 square equals 7. 9 times 10 minus 5 letter 1 D440. Since the dissolution stoichiometry shows 1 mole of copper, I ion, and 1 mole of bromide ion are produced for each moles of Br dissolved, the molar solubility of Cu-Br is 7. 9 times 10 5m. Check your learning. The Ksb of Ag is 1 5 times 10 16. Calculate the molar solubility of silver iodide. Answer 1 2 times 10 8m. Example 15. 4. Determination of molar solubility from Ksb. The Ksb of calcium hydroxide, Ca(O2), is 1 3 times 10 6. Calculate the molar solubility of calcium hydroxide. Solution: the dissolution equation and solubility product expression are Ca(O2), letter 1 D460, Ca2 plus, letter 1 D44, letter 1 D45E, plus 2O minus, letter 1 D44, letter 1 D45E. Ca. The ICE table for this system is: this table has 2 main columns and 4 rows. The first row for the first column does not have a heading and then has the following in the first column: initial concentration, M, change, M, and equilibrium concentration, M. The second column has the header of CaOH, subscript 2 equilibrium arrow C, a superscript 2 positive sign, plus 2OH superscript negative sign. Under the second column is a subgroup of 3 rows and 3 columns. The first column is blank. The second column has the following: 0, positive X, X. The third column has the following: 0, positive 2X, 2X. substituting terms for the equilibrium concentrations into the solubility product expression, and solving for x gives letter 1d43 ESB equals Ka 2 plus O minus 2 1. 3 times 10 minus 6 equals letter 1d465. 2 letter 1d465 2 equals letter 1d465. 4 letter 1d465 2 equals 4 letter 1d465 3 letter 1d465 equals 1. 3 times 10 minus 64 square 3 equals 6. As defined in the ICE table, X is the molarity of calcium ion in the saturated solution. The dissolution stoichiometry shows a 1 relation between moles of calcium ion in solution and moles of compound dissolved, and so the molar solubility of KO2 is 69 times 10^3 m. Check your learning. The KSB of PbI2 is 14 times 10^8. Calculate the molar solubility of lead, Roman 2 iodide. Answer: 15 times 10^3 m. Example 15. 5. Determination of KSB from gram solubility. Many of the pigments used by artists in oil-based paints, figure 15.3, are sparingly soluble in water. For example, the solubility of the artist's pigment chrome yellow, PbCrO4, is 46 times 10^6 gl. Determine the solubility product for PbCrO4. A photograph is shown of a portion of an oil painting which reveals colors of orange, brown, yellow, green, blue, and purple colors in its strokes. A few water droplets rest on the surface. Figure 15. 3 oil paints contain pigments that are very slightly soluble in water. In addition to chrome yellow, PbCrO4, examples include Prussian blue, Fe7, CN18, the reddish-orange color vermilion, HGS, and green color viridian, Cr2O3. Credit: Sunny Abasami's solution. Before calculating the solubility product, the provided solubility must be converted to molarity. PbCrO4 equals 4. 6 times 10 minus 6 g PbCrO41 L times 1 mol PbCrO 4323. 2 g PbCrO4 equals 1. 4 times 10 minus 8 mol PbCrO41 L equals 1. 4 times 10 minus 8 letter 1d440. The dissolution equation for this compound is PbCrO4, letter 1d460, Pb2 plus, letter 1d44 letter 1d45e, plus CrO42 minus letter 1d44 letter 1d45e. The dissolution stoichiometry shows a 1 relation between the molar amounts of compound and its two ions, and so both Pb2 plus and CrO42 minus are equal to the molar solubility of PbCrO4. Pb2 plus equals Cr042 minus equals 1. 4 times 10 minus 8 letter 1d440 KSB equals Pb2 plus Cr042 minus equals 1. 4 times 10 8, 1. 4 times 10 8 equals 2 times 10 16. Check your learning. The solubility of TlCl thallium, I chloride, an intermediate formed when thallium is being isolated from ores, is 3.12 grams per liter at 20 degrees C. What is its solubility product? Answer: 169 times 10 4. Example 15. 6. Calculating the solubility of Hg to Cl2. Calomel, Hg to Cl2, is a compound composed of the diatomic ion of mercury, I, Hg22+, and chloride ions, Cl. Although most mercury compounds are now known to be poisonous, 18th century physicians used calomel as a medication. Their patients rarely suffered any mercury poisoning from the treatments because calomel has a very low solubility, as suggested by its very small KSB. Hg to Cl2, letter 1d460 Hg 22+, letter 1d44 letter 1d45e, plus 2 Cl minus, letter 1d44 letter 1d45e, letter 1d43sb equals 1. 1 times 10 minus 18. Calculate the molar solubility of Hg to Cl2. Solution: the the dissolution stoichiometry shows a 1 relation between the amount of compound dissolved and the amount of mercury, I ions, and so the molar solubility of Hg to Cl2 is equal to the concentration of Hg22 plus ions. Following the ice approach results in this table has 2 main columns and 4 rows. The first row for the first column does not have a heading and then has the following in the first column: initial concentration, M, change, M, equilibrium concentration, M. The second column has the header of Hg subscript 2 Cl subscript 2, equilibrium arrow Hg subscript 2, superscript 2, positive sign, plus 2 Cl superscript negative sign. Under the second column is a subgroup of 3 rows and 3 columns. The first column is blank. The second column has the following: 0, positive XX. The third column has the following: 0, positive 2x, 2x. Substituting the equilibrium concentration terms into the solubility product expression, and solving for x gives letter 1d43 ESB equals Hg 22 plus Cl minus 2 1. 1 times 10 minus 18 equals letter 1d465, 2 letter 1d465 2, 4 letter 1d4653 equals 1. 1 times 10 minus 18 letter 1d465 equals 1. 1 times 10 minus 184 square 3 equals 6. 5 times 10 minus 7 letter 1d440 Hg 22 plus equals 6. 5 times 10 minus 7 letter 1d440 equals 6. 5 times 10 minus 7 letter 1d440 Cl minus equals 2 letter 1d465 equals 2, 6. 5 times 10 minus 7 equals 1. The dissolution stoichiometry shows the molar solubility of Hg to Cl2 is equal to Hg22 plus, or 6. 5 times 10 7 m. Check your learning. Determine the molar solubility of MgF2 from its solubility product. KSB equals 6 4 times 10 9. Answer: 1. 2 times 10 3 m. How sciences interconnect using barium sulfate for medical imaging. Various types of medical imaging techniques are used to aid diagnoses of illnesses in a non-invasive manner. One such technique utilizes the ingestion of a barium compound before taking an X-ray image. A suspension of barium sulfate, a chalky powder, is ingested by the patient. Since the KSB of barium sulfate is 8 times 10 10, very little of it dissolves as it coats the lining of the patient's intestinal tract. Barium-coated areas of the digestive tract then appear on an X-ray as white, allowing for greater visual detail than a traditional X-ray, figure 15. 4. This figure contains one image. A black and white abdominal X-ray image is shown in which the intestinal tract of a person is clearly visible in white, figure 15. 4. A suspension of barium sulfate coats the intestinal tract, permitting greater visual detail than a traditional X-ray. Credit modification of work by Glitzy Queen 00/Wikimedia Commons. Medical imaging using barium sulfate can be used to diagnose acid reflux disease, Crohn's disease, and ulcers in addition to other conditions. Visit this website for more information on how barium is used in medical diagnoses and which conditions it is used to diagnose. Predicting precipitation, the equation that describes the equilibrium between solid calcium carbonate and its solvated ions is Ca-CO3, letter 1d460, Ca2 plus, letter 1d44, letter 1d45e plus, Co32 minus, letter 1d44, letter 1d45e, letter 1d43, letter 1d460, letter 1d45d equals Ca2 plus Co32 minus equals 8. 7 times 10 minus 9. It is important to realize that this equilibrium is established in any aqueous solution containing Ca2 plus and Co32 ions, not just in a solution formed by saturating water with calcium carbonate. Consider, for example, mixing aqueous solutions of the soluble compounds sodium carbonate and calcium nitrate. If the concentrations of calcium and carbonate ions in the mixture do not yield a reaction quotient, QSB, that exceeds the solubility product, KSB, then no precipitation will occur. If the ion concentrations yield a reaction quotient greater than the solubility product, then precipitation will occur, lowering those concentrations until equilibrium is established. QSB equals KSB. The comparison of QSB to KSB to predict precipitation is an example of the general approach to predicting the direction of a reaction first introduced in the chapter on equilibrium. For the specific case of solubility equilibria, QSB-KSB, the reaction proceeds in the forward direction, solution is not saturated, no precipitation observed, QSB-KSB. The reaction proceeds in the reverse direction, solution is supersaturated, precipitation will occur. This predictive strategy and related calculations are demonstrated in the next few example exercises. Example 15. 7. Precipitation of Mg. O2. The first step in the preparation of magnesium metal is the precipitation of Mg. O2 from seawater by the addition of lime, Ca, O2, a readily available inexpensive source of OH ion. MgO2, letter 1D460. Mg2 plus, letter 1D44E, letter 1D45E, plus 2O minus, letter 1D44E, letter 1D45E, letter 1D43ESB equals 8. 9 times 10 minus 12, the concentration of Mg2 plus, AC in seawater is 0. 537 m will Mg. O2 precipitate when enough Ca-O2 is added to give a O of 0. 10 m. Solution calculation of the reaction quotient under these conditions is shown here. Letter 1D444 equals Mg2 plus O minus 2 equals 0. 0537, 0. 0010, 2 equals 5. 4 times 10 minus 8 because Q is greater than KSB. Q equals 5. 4 times 10, 8 is larger than KSB equals 8. 9 times 10, 12. The reverse reaction will proceed, precipitating magnesium hydroxide until the dissolved ion concentrations have been sufficiently lowered, so that QSB equals KSB. Check your learning predict whether Ca-HPO4 will precipitate from a solution with Ca2 plus equals 0, 1 m, and HPO 42 minus equals 0. 1 m answer. No precipitation of Ca-HPO4. Q equals 1 times 10, 7, which is less than KSB. 7 times 10, 7, example 15. 8. Precipitation of AgCl does silver chloride precipitate when equal volumes of a 2 times 10 4m solution of AgNO3 and a 2 times 10 4m solution of NaCl are mixed. Solution. The equation for the equilibrium between solid silver chloride, silver ion, and chloride ion is AgCl, letter 1D460, Ag plus, letter 1D44E, letter 1D45E plus Cl minus, letter 1D44E, letter 1D45E. The solubility product is 1. 6 times 10, 10, see Appendix J. AgCl will precipitate if the reaction quotient calculated from the concentrations in the mixture of AgNO3 and NaCl is greater than KSB. Because the volume doubles when equal volumes of AgNO3 and NaCl solutions are mixed, each concentration is reduced to half its initial value 12, 2. 0 times 10 minus 4 letter 1D440 equals 1. The reaction quotient Q is greater than KSB for AgCl, so a supersaturated solution is formed. Letter 1D444 equals Ag plus Cl minus equals 1. 0 times 10 minus 4, 1. 0 times 10 minus 8 letter 1D43ESB AgCl will precipitate from the mixture until the dissolution equilibrium is established, with Q equal to KSB. Check your learning. Will KClO4 precipitate when 20 ml of a 0, 50 m solution of K plus is added to 80 ml of a 0, 50 m solution of ClO4 minus? Hint: Use the dilution equation to calculate the concentrations of potassium and perchlorate ions in the mixture. Answer: no, Q equals 4 times 10 3, which is less than KSB equals 1. 5 times 10 2. Example 15, 9. Precipitation of calcium oxalate. Blood will not clot if calcium ions are removed from its plasma. Some blood collection tubes contain salts of the oxalate ion, C2O42-. For this purpose, figure 15. 5. At sufficiently high concentrations, the calcium and oxalate ions form solid, Ca-C2O4H2O, calcium oxalate monohydrate. The concentration of Ca2+ in a sample of blood serum is 2 times 10^3 m. What concentration of C2O42-? Ion must be established before Ca-C2O4H2O begins to precipitate. A photograph is shown of 6 vials of blood resting on and near a black and white document. 2 of the vials have purple caps, 3 have tan caps, and 1 has a red cap. Each has a label, and the vials with tan caps have a small amount of an off-white material present in a layer at the base of the vial. Figure 15. 5 anticoagulants can be added to blood that will combine with the Ca2+ ions in blood serum and prevent the blood from clotting. Credit, modification of work by Nita Lind. Solution. The equilibrium expression is Ca-C2O4, letter 1D460, Ca2+, letter 1D44E, letter 1D45E, plus C2O42-, letter 1D44E, letter 1D45E. For this reaction, letter 1D43SB equals Ca2 plus C2O42- equals 1. 96 times 10⁻⁹. See Appendix J. Substitute the provided calcium ion concentration into the solubility product expression and solve for oxalate concentration. Letter 1D444 equals letter 1D43SB equals Ca2 plus C2O42- equals 1. 96 times 10⁻⁹. 2 times 10⁻�3, C2O42- equals 1. 96 times 10⁻⁹. C2O42- equals 1. 96 times 10⁻92. 2 times 10⁻3 equals 8. 9 times 10⁻7, letter 1D440. A concentration of C2O42- equals 8. 9 times 10⁷ m is necessary to initiate the precipitation of Ca-C2O4 under these conditions. Check your learning. If a solution contains 0.20 mol of CrO42- per liter, what concentration of Ag plus ion must be reached by adding solid Ag NO3 before Ag2CrO4 begins to precipitate? Neglect any increase in volume upon adding the solid silver nitrate. Answer: 6-7 times 10⁵ m. Example 15, 10. Concentrations following precipitation. Clothing washed in water that has a manganese Mn2+, Ac, concentration exceeding 0.1 mg/L 18 times 10⁶ m, may be stained by the manganese upon oxidation, but the amount of Mn2+ in the water can be decreased by adding a base to precipitate MnO2. What pH is required to keep Mn2+ equal to 1/8 times 10⁶ m? Solution. The dissolution of MnO2 is described by the equation MnO2, letter 1D460, Mn2+, letter 1D44E, letter 1D45E, plus 2O-, letter 1D44E, letter 1D45E, letter 1D43SB equals 2 times 10⁻13. At equilibrium, letter 1D43SB equals Mn2 plus O-2. Or 1, 8 times 10⁻6, O-2 equals 2 times 10⁻13. So, O- equals 3. 3 times 10⁻4, letter 1D440. Calculate the pH from the pOH. pOH equals minus log O minus equals minus log 3. 3 times 10⁻4 equals 3. 48 pH equals 14. 0 minus PO equals 14. 0 minus 3. 48 equals 10. 52. Final result, rounded to one significant digit, limited by the certainty of the KSB. Check your learning. The first step in the preparation of magnesium metal is the precipitation of MgO2 from seawater by the addition of Ka(O2). The concentration of Mg2+ AC in seawater is 537 times 10^2 m. Calculate the pH at which Mg2+ is decreased to 1 times 10^5 m. Answer 1097. In solutions containing two or more ions that may form insoluble compounds with the same counter-ion, an experimental strategy called selective precipitation may be used to remove individual ions from solution. By increasing the counter-ion concentration in a controlled manner, ions in solution may be precipitated individually, assuming their compound solubilities are adequately different. In solutions with equal concentrations of target ions, the ion forming the least soluble compound will precipitate first, at the lowest concentration of counter-ion, with the other ions subsequently precipitating as their compound solubilities are reached. As an illustration of this technique, the next example exercise describes separation of a two halide ions via precipitation of one as a silver salt. Chemistry in everyday life. The role of precipitation in wastewater treatment. Solubility equilibria are useful tools in the treatment of wastewater, carried out in facilities that may treat the municipal water in your city or town. Figure 15. 6. Specifically, selective precipitation is used to remove contaminants from wastewater before it is released back into natural bodies of water. For example, phosphate ions, Po43-, are often present in the water discharged from manufacturing facilities. An abundance of phosphate causes excess algae to grow, which impacts the amount of oxygen available for marine life, as well as making water unsuitable for human consumption. A color photograph is shown of a high-volume wastewater treatment facility. 19 large circular pools of water undergoing treatment are visible across the center of the photograph. A building and parking lot are visible in the foreground. Figure 15. 6 wastewater treatment facilities, such as this one, remove contaminants from wastewater before the water is released back into the natural environment. Credit, Eutrophication and Hypoxia /Wikimedia Commons. One common way to remove phosphates from water is by the addition of calcium hydroxide or lime Ka(O2). As the water is made more basic, the calcium ions react with phosphate ions to produce hydroxylapatite, Ka5, Po4,3O, which then precipitates out of the solution. 5Ka2 plus 3 Po43 minus plus O minus Ka5, Po4,3O, letter 1D460. Because the amount of calcium ion added does not result in exceeding the solubility products for other calcium salts, the anions of those salts remain behind in the wastewater. The precipitate is then removed by filtration, and the water is brought back to a neutral pH by the addition of CO2 in a recarbonation process. Other chemicals can also be used for the removal of phosphates by precipitation, including iron, Roman-3, chloride, and aluminum sulfate. View this site for more information on how phosphorus is removed from wastewater. Example 15. 11. Precipitation of silver halides. A solution contains 0.10 mol of KBr and 0.10 mol of KCl per liter. AgNO3 is gradually added to this solution, which forms first solid AgBr or solid AgCl solution. The two equilibria involved are AgCl, letter 1D460 Ag plus, letter 1D44E, letter 1D45E plus Cl minus, letter 1D44E, letter 1D45E Ag Br, letter 1D460 Ag plus, letter 1D44E, letter 1D45E plus Br minus, letter 1D44E, letter 1D45E, letter 1D43Sb, letter 1D43Sb equals 1. 6 times 10 minus 105, 0 times 10 minus 13. If the solution contained about equal concentrations of Cl and Br, Then the silver salt with the smaller KSB, Ag-Br, would precipitate first. The concentrations are not equal, however, so the Ag+, at which AgCl begins to precipitate, and the Ag+, at which Ag-Br begins to precipitate, must be calculated. The salt that forms at the lower Ag+ precipitates first. Ag-Br precipitates when Q equals KSB for Ag-Br. Ag-Br Ag 00010 equals 5, 0 times 10 minus 13. Ag plus equals 5, 0 times 10 minus 130, 00010 equals 5. 0 times 10 minus 9, letter 1D440. Ag-Br begins to precipitate when Ag plus is 5 times 10(9m) for AgCl. AgCl precipitates when Q equals KSB for AgCl 1. 6 times 10(10) when Cl equals 0. 10m, letter 1D444SB equals letter 1D43SB equals Ag plus Cl minus equals Ag plus equals 1. 6 times 10 minus 10. Ag plus equals 1. 6 times 10 minus 100. 10 equals 1. 6 times 10 minus 9, letter 1D440. AgCl begins to precipitate when Ag plus is 1. 6 times 10(9m), AgCl begins to precipitate at a lower Ag plus than Ag-Br, so AgCl begins to precipitate first. Note the chloride ion concentration of the initial mixture was significantly greater than the bromide ion concentration, and so silver chloride precipitated first despite having a KSB greater than that of silver bromide. Check your learning. If silver nitrate solution is added to a solution which is 0.50m in both Cl and Br ions, at what Ag plus would precipitation begin, and what would be the formula of the precipitate? Answer. Ag plus equals 1 times 1011m. Ag-Br precipitates first. Common ion effect. Compared with pure water, the solubility of an ionic compound is less in aqueous solutions containing a common ion, one also produced by dissolution of the ionic compound. This is an example of a phenomenon known as the common ion effect, which is a consequence of the law of mass action that may be explained using Le Ch-Atlier's principle. Consider the dissolution of silver iodide. Ag-I, letter 1D460 Ag plus, letter 1D44E, letter 1D45E plus, I minus, letter 1D44E, letter 1D45E. This solubility equilibrium may be shifted left by the addition of either silver, I, or iodide ions, resulting in the precipitation of Ag-I and lowered concentrations of dissolved Ag plus and I. In solutions that already contain either of these ions, less Ag-I may be dissolved than in solutions without these ions. This effect may also be explained in terms of mass action as represented in the solubility product expression. Ag-I, the mathematical product of silver, I and iodide ion molarities, is constant in an equilibrium mixture regardless of the source of the ions, and so an increase in one ion's concentration must be balanced by a proportional decrease in the other. Link to learning. View this simulation to explore various aspects of the common ion effect. Example 15. 12. Common ion effect on solubility. What is the effect on the amount of solid Mg(O2) and the concentrations of Mg2+ and OH when each of the following are added to a saturated solution of Mg(O2)? A. MgCl2, B. KOA, C. NuO3, D. MgO2. Solution. The solubility equilibrium is MgO2, letter 1D460, Mg2+, letter 1D44, letter 1D45E, plus 2O-, letter 1D44, letter 1D45E. A. Adding a common ion, Mg2+, will increase the concentration of this ion and shift the solubility equilibrium to the left, decreasing the concentration of hydroxide ion and increasing the amount of undissolved magnesium hydroxide. B. Adding a common ion, OH, will increase the concentration of this ion and shift the solubility equilibrium to the left, decreasing the concentration of magnesium ion and increasing the amount of undissolved magnesium hydroxide. C. The added compound does not contain a common ion, and no effect on the magnesium hydroxide solubility equilibrium is expected. D. Adding more solid magnesium hydroxide will increase the amount of undissolved compound in the mixture. The solution is already saturated, though, so the concentrations of dissolved magnesium and hydroxide ions will remain the same, MgO. Thus, changing the amount of solid magnesium hydroxide in the mixture has no effect on the value of Q, and no shift is required to restore Q to the value of the equilibrium constant. Check your learning. What is the effect on the amount of solid NiCO3 and the concentrations of Ni2+ and CO32- when each of the following are added to a saturated solution of NiCO3? A. NiNO32, B. KClO4, C. NiCO3, D. KTCO3. Answer: A. Mass of NiCO3 S increases, Ni2+ increases, CO32- decreases. B. No appreciable effect. C. No effect except to increase the amount of solid NiCO3. D. Mass of NiCO3 S increases, Ni2+ decreases, CO32- increases. Example 15, 13. Common ion effect. Calculate the molar solubility of cadmium sulfide, CdS, in a 0.10 m solution of cadmium bromide, CdBr2. The Ksb of CdS is 1 times 1028 solution. This calculation can be performed using the ICE approach. CdS, letter 1d460, Cd2+, letter 1d44e, letter 1d45e, plus S2-, letter 1d44e, letter 1d45e. This table has 2 main columns and 4 rows. The first row for the first column does not have a heading and then has the following in the first column: initial concentration, M, change, M, and equilibrium concentration, M. The second column has the header, CdS equilibrium arrow CD to the second power plus S to the second power superscript negative sign. Under the second column is a subgroup of 3 rows and 3 columns. The first column is blank. The second column has the following: 010 positive X, 010 plus X. The third column has the following: 0 positive X, X. Letter 1d43 ESB equals CD2 plus S2 minus equals 1. 0 times 10 minus 28. 0, 0, 10 plus letter 1d465. Letter 1d465 equals 1. 0 times 10 minus 28. Because Ksb is very small, assume x 0, 10 and solve the simplified equation for x 0, 0, 10. Letter 1d465 equals 1. 0 times 10 minus 28. Letter 1d465 equals 1. 0 times 10 minus 26. Letter 1d440. The molar solubility of CdS in this solution is 1 times 1026 m. Check your learning. Calculate the molar solubility of aluminum hydroxide, AlO3, in a 0.15 m solution of aluminum nitrate, AlNO33. The Ksb of AlO3 is 2 times 1032. Answer: 4 times 1011 m. Learning objectives. By the end of this section, you will be able to explain the Lewis model of acid-base chemistry, write equations for the formation of adducts and complex ions, perform equilibrium calculations involving formation constants. In 1923, G. N. Lewis proposed a generalized definition of acid-base behavior, in which acids and bases are identified by their ability to accept or to donate a pair of electrons and form a coordinate covalent bond. A coordinate covalent bond, or dative bond, occurs when one of the atoms in the bond provides both bonding electrons. For example, a coordinate covalent bond occurs when a water molecule combines with a hydrogen ion to form a hydronium ion. A coordinate covalent bond also results when an ammonia molecule combines with a hydrogen ion to form an ammonium ion. Both of these equations are shown here. This figure shows two reactions represented with Lewis structures. The first shows an O atom bonded to two H atoms. The O atom has two lone pairs of electrons. There is a plus sign, and then an H atom with a superscript positive sign, followed by a right-facing arrow. The next Lewis structure is in brackets and shows an O atom bonded to three H atoms. There is one lone pair of electrons on the O atom. Outside of the brackets is a superscript positive sign. The second reaction shows an N atom bonded to three H atoms. The N atom has one lone pair of electrons. There is a plus sign and then an H superscript positive sign. After the H superscript positive sign is a right-facing arrow. The next Lewis structure is in brackets. It shows an N atom bonded to four H atoms. There is a superscript positive sign outside the brackets. Reactions involving the formation of coordinate covalent bonds are classified as Lewis acid-base chemistry. The species donating the electron pair that compose the bond is a Lewis base. The species accepting the electron pair is a Lewis acid, and the product of the reaction is a Lewis acid-base adduct. As the two examples above illustrate, Bronsted-Lowry acid-base reactions represent a subcategory of Lewis acid reactions, specifically those in which the acid species is H+. A few examples involving other Lewis acids and bases are described below. The boron atom in boron trifluoride, Bf3, has only 6 electrons in its valence shell. Being short of the preferred octet, Bf3 is a very good Lewis acid and reacts with many Lewis bases. A fluoride ion is the Lewis base in this reaction, donating one of its lone pairs. This figure illustrates a chemical reaction using structural formulas. On the left, an F atom is surrounded by 4 electron dot pairs and has a superscript negative symbol. This structure is labeled below as Lewis base. Following a plus sign is another structure which has a B atom at the center and 3 F atoms single bonded above, right, and below. Each F atom has 3 pairs of electron dots. This structure is labeled below as Lewis acid. Following a right-pointing arrow is a structure in brackets that has a central B atom to which 4 F atoms are connected with single bonds above, below, to the left, and to the right. Each F atom in this structure has 3 pairs of electron dots. Outside the brackets is a superscript negative symbol. This structure is labeled below as acid-base adduct. In the following reaction, each of 2 ammonia molecules, Lewis bases, donates a pair of electrons to a silver ion, the Lewis acid. This figure illustrates a chemical reaction using structural formulas. On the left side, a 2 precedes an N atom which has H atoms single bonded above, to the left, and below. A single electron dot pair is on the right side of the N atom. This structure is labeled below as Lewis base. Following a plus sign is an Ag atom which has a superscript plus symbol. Following a right-pointing arrow is a structure in brackets that has a central Ag atom to which N atoms are connected with single bonds to the left and to the right. Each of these N atoms has H atoms bonded above, below, and to the outside of the structure. Outside the brackets is a superscript plus symbol. This structure is labeled below as acid-base adduct. Nonmetal oxides act as Lewis acids and react with oxide ions, Lewis bases, to form oxyanions. This figure illustrates a chemical reaction using structural formulas. On the left, an O atom is surrounded by 4 electron dot pairs and has a superscript 2 negative. This structure is labeled below as Lewis base. Following a plus sign is another structure which has an S atom at the center. O atoms are single bonded above and below. These O atoms have 3 electron dot pairs each. To the right of the S atom is a double bonded O atom which has 2 pairs of electron dots. This structure is labeled below as Lewis acid. Following a right pointing arrow is a structure in brackets that has a central S atom to which 4 O atoms are connected with single bonds above, below, to the left, and to the right. Each of the O atoms has 3 pairs of electron dots. Outside the brackets is a superscript 2 negative. This structure is labeled below as acid-base adduct. Many Lewis acid-base reactions are displacement reactions, in which one Lewis base displaces another Lewis base from an acid-base adduct, or in which one Lewis acid displaces another Lewis acid. 2 chemical reactions in 2 rows using structural formulas. First row, to the left, in brackets is a structure with a central Ag atom to which N atoms are connected with single bonds to the left and right. Each N atom has H atoms bonded above, below, and to the outside. Outside the brackets is a superscript plus symbol. This structure is labeled acid-base adduct. Following a plus sign is a 2 and another structure in brackets that shows a C atom triple bonded to an N atom. The C atom has an unshared electron pair on its left side, and the N atom has an unshared pair on its right side. Outside the brackets to the right is a superscript negative symbol. This structure is labeled base. Following a right pointing arrow is a structure in brackets with a central Ag atom to which 4 Fc atoms are connected with single bonds to the left and right. At each of the 2 ends, N atoms are triple bonded to the C atoms. The N atoms each have an unshared electron pair at the end of the structure. Outside the brackets is a superscript negative symbol. This structure is labeled nu adduct. Following a plus sign is an N atom with H atoms single bonded above, to the left, and below. A single electron dot pair is on the left side of the N atom. This structure is labeled nu base. In the second row, on the left side in brackets is a structure with a central C atom. O atoms, each with 3 unshared electron pairs, are single bonded above and below, and a third O atom with 2 unshared electron pairs is double bonded to the right. Outside the brackets is a superscript 2 negative. This structure is labeled acid-base adduct. Following a plus sign is another structure with an S atom at the center. O atoms are single bonded above and below. These O atoms have 3 electron dot pairs each. To the right of the S atom is a double bonded O atom which has 2 pairs of electron dots. This structure is labeled acid. Following a right pointing arrow is a structure in brackets with a central S atom, to which 4 O atoms are connected with single bonds above, below, left, and right. Each of the O atoms has 3 pairs of electron dots. Outside the brackets is a superscript 2 negative. This structure is labeled nu adduct. Following a plus sign is a structure with a central C atom that has 2 O atoms, each with 2 unshared electron pairs, double bonded to the left and right. Another type of Lewis acid-base chemistry involves the formation of a complex ion, or a coordination complex, comprising a central atom, typically a transition metal cation, surrounded by ions or molecules called ligands. These ligands can be neutral molecules like H2O or NH3, or ions such as CN or O. Often, the ligands act as Lewis bases, donating a pair of electrons to the central atom. These types of Lewis acid-base reactions are examples of a broad subdiscipline called coordination chemistry, the topic of another chapter in this text. The equilibrium constant for the reaction of a metal ion with one or more ligands to form a coordination complex is called a formation constant, Kf, sometimes called a stability constant. For example, the complex ion Cu, Cn2-. A Cu atom is bonded to 2 C atoms. Each of these C atoms is triple bonded to an N atom. Each N atom has 2 dots on the side of it. Is produced by the reaction Cu plus, letter 1d44e, letter 1d45e, plus 2 Cn minus, letter 1d44e, letter 1d45e, Cu, Cn2 minus, letter 1d44e, letter 1d45e. The formation constant for this reaction is Letter 1d43F equals Q, Cn2 minus Q plus Cn minus 2. Alternatively, the reverse reaction, decomposition of the complex ion, can be considered, in which case the equilibrium constant is a dissociation constant, Kd. Per the relation between equilibrium constants for reciprocal reactions described, the dissociation constant is the mathematical inverse of the formation constant, Kd equals Kf1. A tabulation of formation constants is provided in Appendix K as an example of dissolution by complex ion formation. Let us consider what happens when we add aqueous ammonia to a mixture of silver chloride and water. Silver chloride dissolves slightly in water, giving a small concentration of Ag+. Ag+ equals 1 3 times 10^5 m. AgCl, letter 1d460, Ag+, letter 1d44e, letter 1d45e plus Cl minus, letter 1d44e, letter 1d45e. However, if NH3 is present in the water, the complex ion Ag NH3 2+ can form according to the equation Ag+, letter 1d44e, letter 1d45e, plus 2 NH3, letter 1d44e, letter 1d45e Ag, NH3 2+, letter 1d44e, letter 1d45e, with letter 1d43F equals Ag, NH3, 2 plus Ag plus NH3 2 equals 1. 7 times 107. The large size of this formation constant indicates that most of the free silver ions produced by the dissolution of AgCl combine with NH3 to form Ag, NH3, 2+. As a consequence, the concentration of silver ions Ag+ is reduced, and the reaction quotient for the dissolution of silver chloride, Ag plus Cl, falls below the solubility product of AgCl. AgCl, more silver chloride then dissolves. If the concentration of ammonia is great enough, all of the silver chloride dissolves. Example 15. 14. Dissociation of a complex ion. Calculate the concentration of the silver ion in a solution that initially is 0. 10 m with respect to Ag NH3 2+. Solution. Applying the standard ice approach to this reaction yields the following. This table has 2 main columns and 4 rows. The first row for the first column does not have a heading and then has the following in the first column: initial concentration m, change m, and equilibrium concentration m. The second column has the header, a G superscript positive sign plus 2 NH subscript 3 equilibrium sign, a G NH subscript 3, subscript 2 superscript positive sign. Under the second column is a subgroup of 3 rows and 3 columns. The first column contains 0, positive XX. The second column contains 0, positive 2x, 2x. The third column contains 0, 10, negative x, and 0, 10 minus x. Substituting these equilibrium concentration terms into the Kf expression gives letter 1d43F equals Ag, NH3 2 plus Ag plus NH3 2. 1. 7 times 107 equals 0. 10 minus letter 1d465, letter 1d465, 2 letter 1d465 2. The very large equilibrium constant means the amount of the complex ion that will dissociate, X, will be very small. Assuming X01 permits simplifying the above equation, 7 times 107 equals 0. 10, letter 1d465, 2 letter 1d465 2. Letter 1d465 3 equals 0. 104 1. 7 times 107 equals 1. 5 times 10 minus 9. Letter 1d465 equals 1. 5 times 10 minus 9 square 3 equals 1. 1 times 10 minus 3. Because only 1% of the Ag, NH3, 2+, dissociates into Ag plus and NH3, the assumption that X is small is justified. Using this value of X and the relations in the above ice table allows calculation of all species, equilibrium concentrations. Ag plus equals 0 plus letter 1d465 equals 1. 1 times 10 minus 3, letter 1d440. NH3 equals 0, plus 2 letter 1d465 equals 2. 2 times 10 minus 3, letter 1d440. Ag NH3 2 plus equals 0. 10 minus letter 1d465 equals 0. 10 minus 0. 0011 equals 0. 99. The concentration of free silver ion in the solution is 0. 11 m. Check your learning. Calculate the silver ion concentration, Ag+, of a solution prepared by dissolving 1 g of Ag no 3 and 10 0 g of KCN in sufficient water to make 1 L of solution. Hint: because Kf is very large, the silver cyanide complex ion C appendix K, assume the reaction goes to completion and then calculate the Ag+ produced by dissociation of the complex. Answer 2 9 times. 1022 m. Learning objectives. By the end of this section, you will be able to describe examples of systems involving 2 or more coupled chemical equilibria, calculate reactant and product concentrations for coupled equilibrium systems. As discussed in preceding chapters on equilibrium, coupled equilibria involve 2 or more separate chemical reactions that share 1 or more reactants or products. This section of this chapter will address solubility equilibria coupled with acid-base and complex formation reactions. An environmentally relevant example illustrating the coupling of solubility and acid-base equilibria is the impact of ocean acidification on the health of the ocean's coral reefs. These reefs are built upon skeletons of sparingly soluble calcium carbonate excreted by colonies of corals, small marine invertebrates. The relevant dissolution equilibrium is Ca-CO3, letter 1d460, Ca2 plus, letter 1d44, letter 1d45e plus, CO3 minus 2, letter 1d44, letter 1d45e, letter 1d43 ESB equals 8. 7 times 10 minus 9. Rising concentrations of atmospheric carbon dioxide contribute to an increased acidity of ocean waters due to the dissolution, hydrolysis, and acid ionization of carbon dioxide. CO2 letter 1d454, CO2 letter 1d44, letter 1d45e, CO2 letter 1d44, letter 1d45e, plus H2O, letter 1d459 H2CO 3, letter 1d44, letter 1d45e, H2CO 3, letter 1d44, letter 1d45e, plus H2O, letter 1d459 HCO 3 minus letter 1d44, letter 1d45e, plus H3O plus, letter 1d44, letter 1d45e, letter 1d43e, a 1 equals 4. 3 times 10 minus 7. HCO 3 minus, letter 1d44, letter 1d45e, plus H2O, letter 1d459, CO 32 minus, letter 1d44, letter 1d45e, plus H3O plus letter 1d44, letter 1d45e, letter 1d43e, a 2 equals 4. 7 times 10 minus 11. Inspection of these equilibria shows the carbonate ion is involved in the calcium carbonate dissolution and the acid hydrolysis of bicarbonate ion. Combining the dissolution equation with the reverse of the acid hydrolysis equation yields Ca-CO3, letter 1d460, plus H3O plus, letter 1d44, letter 1d45e, Ca2 plus, letter 1d44, letter 1d45e, plus HCO3 minus, letter 1d44, letter 1d45e, plus H2O, letter 1d459, letter 1d43e equals letter 1d43sb slash letter 1d43e, a 2 equals 180. The equilibrium constant for this net reaction is much greater than the Ksb for calcium carbonate, indicating its solubility is markedly increased in acidic solutions. As rising carbon dioxide levels in the atmosphere increase the acidity of ocean waters, the calcium carbonate skeletons of coral reefs become more prone to dissolution and subsequently less healthy. Figure 15.7. This figure contains 2 photographs of coral reefs. In a colorful reef that includes hues of purple and pink corals is shown in blue-green water with fish swimming in the background. In B, Gray-green mossy-looking coral is shown in a blue aquatic environment. This photo does not have the colorful appearance or fish that were shown in Figure A. Figure 15. 7 healthy coral reefs, A, support a dense and diverse array of sea life across the ocean food chain. But when coral are unable to adequately build and maintain their calcium carbonate skeletons because of excess ocean acidification, the unhealthy reef B is only capable of hosting a small fraction of the species as before, and the local food chain starts to collapse. Credit A, modification of work by NOAA Photo Library. Credit B, modification of work by Prillfish/Flickr. Link to learning. Learn more about ocean acidification and how it affects other marine creatures. This site has detailed information about how ocean acidification specifically affects coral reefs. The dramatic increase in solubility with increasing acidity described above for calcium carbonate is typical of salts containing basic anions e.g., carbonate, fluoride, hydroxide, sulfide. Another familiar example is the formation of dental cavities in tooth enamel. The major mineral component of enamel is calcium hydroxyapatite, Figure 15. 8. A sparingly soluble ionic compound, whose dissolution equilibrium is Ca5, Po430, letter 1D460, 5 Ca2+, letter 1D44, letter 1D45E, plus 3 Po43 minus, letter 1D44, letter 1D45E, plus O minus, letter 1D44, letter 1D45E. This figure includes an image of 2 large light blue apatite crystals in a mineral conglomerate that includes white, gray, and tan crystals. The blue apatite crystals have a dull, dusty, or powdered appearance. Figure 15. 8 crystal of the mineral hydroxyapatite Ca5, Po430 is shown here. The pure compound is white, but like many other minerals, this sample is colored because of the presence of impurities. This compound dissolved to yield 2 different basic ions, triprotic phosphate ions, Po43-, letter 1D44, letter 1D45E, plus H3O+, letter 1D44, letter 1D45E, H2Po42-, letter 1D44, letter 1D45E, plus H2O, letter 1D459, HPO, H2Po4-, letter 1D44, letter 1D45E, plus H3O+, letter 1D44, letter 1D45E, H3Po4, letter 1D44, letter 1D45E, plus H2O, letter 1D459. And monoprotic hydroxide ions, O-, letter 1D44, letter 1D45E, plus H3O plus 2H2O. Of the 2 basic productions, the hydroxide is, of course, by far the stronger base. It's the strongest base that can exist in aqueous solution. And so, it is the dominant factor providing the compound an acid-dependent solubility. Dental cavities form when the acid waste of bacteria growing on the surface of teeth hastens the dissolution of tooth enamel by reacting completely with the strong base hydroxide, shifting the hydroxyapatite solubility equilibrium to the right. Some toothpastes and mouth rinses contain added NF, or SnF2, that make enamel more acid-resistant by replacing the strong base hydroxide with the weak base fluoride. NaF plus Ca5, Po430 Ca5, Po43F plus Na plus O minus. The weak base fluoride ion reacts only partially with the bacterial acid waste, resulting in a less extensive shift in the solubility equilibrium and an increased resistance to acid dissolution. See the Chemistry and Everyday Life feature on the role of fluoride in preventing tooth decay for more information. Chemistry in Everyday Life. Role of fluoride in preventing tooth decay. As we saw previously, fluoride ions help protect our teeth by reacting with hydroxylapatite to form fluorapatite, Ca5, Po4, 3F. Since it lacks a hydroxide ion, fluorapatite is more resistant to attacks by acids in our mouths and is thus less soluble, protecting our teeth. Scientists discovered that naturally fluorinated water could be beneficial to your teeth, and so it became common practice to add fluoride to drinking water. Toothpastes and mouthwashes also contain amounts of fluoride. Figure 15. 9. Replace with updated art. Figure in 99 art folder is current and correct. Figure 15. 9. Fluoride, found in many toothpastes, helps prevent tooth decay. Credit. Carrie Sessick. Unfortunately, excess fluoride can negate its advantages. Natural sources of drinking water in various parts of the world have varying concentrations of fluoride, and places where that concentration is high are prone to certain health risks when there is no other source of drinking water. The most serious side effect of excess fluoride is the bone disease, skeletal fluorosis. When excess fluoride is in the body, it can cause the joints to stiffen and the bones to thicken. It can severely impact mobility and can negatively affect the thyroid gland. Skeletal fluorosis is a condition that over 27 million people suffer from across the world. So while fluoride can protect our teeth from decay, the U.S. Environmental Protection Agency sets a maximum level of 4 ppm, 4 mg/L, of fluoride in drinking water in the U.S. Fluoride levels in water are not regulated in all countries, so fluorosis is a problem in areas with high levels of fluoride in the groundwater. The solubility of ionic compounds may also be increased when dissolution is coupled to the formation of a complex ion. For example, aluminum hydroxide dissolves in a solution of sodium hydroxide or another strong base because of the formation of the complex ion Al, O4-. An H atom is bonded to an O atom. The O atom has 2 dots above it and 2 dots below it. The O atom is bonded to an Al atom, which has 3 additional O atoms bonded to it as well. Each of these additional O atoms has 4 dots arranged around it and is bonded to an H atom. This entire molecule is contained in brackets, to the right of which is a superscripted negative sign. The equations for the dissolution of aluminum hydroxide, the formation of the complex ion, and the combined net equation are shown below. As indicated by the relatively large value of K for the net reaction, coupling complex formation with dissolution drastically increases the solubility of Al, O3. Al-O, Al3 plus, letter 1d44e, letter 1d45e, plus 3O-, letter 1d44e, letter 1d45e, Al3 plus, letter 1d44e, letter 1d45e, plus 4O-, letter 1d44e, letter 1d45e, Al, O4-, letter 1d44e, letter 1d45e, net. Al O3, letter 1d460, plus O-, letter 1d44e, letter 1d45e, Al, O4-, letter 1d44e, letter 1d45e, letter 1d43esb equals 2 times 10 minus 32, letter 1d43ef equals 1. 1 times 1033, letter 1d43e equals, letter 1d43esb, letter 1d43ef equals 22. Example 15. 15. Increased solubility in acidic solutions. Compute and compare the molar solubilities for aluminum hydroxide, Al, O3, dissolved in a pure water, and B, a buffer containing 0, 100 m acetic acid and 0, 100 m sodium acetate, solution. A, the molar solubility of aluminum hydroxide in water is computed considering the dissolution equilibrium only as demonstrated in several previous examples. Al-O, Al3 plus, letter 1d44e, letter 1d45e, plus 3O-, letter 1d44e, letter 1d45e, letter 1d43esb equals 2 times 10 minus 32 molar solubility in water equals Al3 plus equals 2 times 10 minus 32 slash 27. 1 slash 4 equals 5 times 10 minus 9, letter 1d440. B, the concentration of hydroxide ion of the buffered solution is conveniently calculated by the Henderson-Hasselbalch equation. pH equals pK plus log CH3 Q minus slash CH3 Q pH equals 4. 74 plus log 0. 100 0. 100 equals 4. 74. At this pH, The concentration of hydroxide ion is PO equals 14,004, 74 equals 9, 26 O minus equals 10 minus 9, 26 equals 5. 5 times 10 minus 10. The solubility of AlO3 in this buffer is then calculated from its solubility product expressions. Letter 1D43ESB equals Al3 plus O minus 3 molar solubility in buffer equals Al3 plus equals letter 1D43ESB slash O minus 3 equals 2 times 10 minus 32 slash 5. 5 times 10 minus 10 3 equals 1. 2 times 10 minus 4 letter 1D440. Compared to pure water, the solubility of aluminum hydroxide in this mildly acidic buffer is approximately 10 million times greater, though still relatively low. Check your learning. What is the solubility of aluminum hydroxide in a buffer comprised of 0, 100 m formic acid and 0, 100 m sodium formate? Answer: 0, 1 m. Example 15. 16. Multiple equilibria. Unexposed silver halides are removed from photographic film when they react with sodium thiosulfate NuS2O3, called hypo, to form the complex ion Ag, S2O323-. Kf equals 4. 7 times 1013. A chemical reaction is shown using structural formulas. On the left, a G superscript plus is followed by a plus sign, the number 2, and a structure in brackets. The structure is composed of a central S atom which has O atoms single bonded above, right, and below. A second S atom is single bonded to the left. Each of these bonded atoms has 6 dots around it. Outside the brackets is a superscript 2 negative. Following a bidirectional arrow is a structure in brackets with a central Ag atom. To the left and right, S atoms are single bonded to the Ag atom. Each of these S atoms has 4 dots around it, and an S atom connected with a single bond moving out from the central Ag atom, forming the ends of the structure. Each of these atoms has 3 O atoms attached with single bonds above, below, and at the end of the structure. Each O atom has 6 dots around it. Outside the brackets is a superscript 3 negative. What mass of NuS2O3 is required to prepare 1 L of a solution that will dissolve 1 G of Ag-Br by the formation of Ag, S2O323-. Solution: 2 equilibria are involved when silver bromide dissolves in an aqueous thiosulfate solution containing the S2O32-. Ion dissolution: Ag-Br, letter 1D460, Ag plus, letter 1D44E, letter 1D45E plus Br minus, letter 1D44E, letter 1D45E, letter 1D43ESB equals 5. 0 times 10 minus 13. Complexation: Ag plus, letter 1D44E, letter 1D45E, plus 2S2O32 minus, letter 1D44E, letter 1D45E Ag, S2O323 minus, letter 1D44E, letter 1D45E, letter 1D43F equals 4. 7 times 1013. Combining these two equilibrium equations yields Ag-Br, letter 1D460, plus 2S2O32, letter 1D44E, letter 1D45E, letter 1D43E equals Ag, S2O323 Br, S2O322 equals letter 1D43SB, letter 1D43F, equals 24 Ag, S2O323, letter 1D44E, letter 1D45E, plus Br, letter 1D44E, letter 1D45E. The concentration of bromide resulting from dissolution of 1 G of Ag-Br in 1 L of solution is Br equals 1 G Ag-Br times 1 mol Ag-Br 187. 77 G slash mol times 1 mol Br 1 mol Ag-Br 1. 0 L equals 0. 532 m. The stoichiometry of the dissolution equilibrium indicates the same concentration of aqueous silver ion will result 0. 532 m, and the very large value of letter 1D43F ensures that essentially all the dissolved silver ion will be complexed by thiosulfate ion. Ag SO3 23 equals 0, 532 m. Rearranging the K expression for the combined equilibrium equations and solving for the concentration of thiosulfate ion yields. S2O 32 equals Ag S2O3 23 Br square letter 1 D43 equals 0. 00532 letter 1 D440 0. 00532 letter 1 D440 24 square equals 0. 11 m. Finally, the total mass of nut S2O3 required to provide enough thiosulfate to yield the concentrations cited above can be calculated. Mass of nut S2O3 required to yield 0. 532 m Ag SO2 23. 0. 00532 mol Ag SO3 23 1. 0 L times 2 mol S2O 32 1 mol Ag SO3 23 times 1 mol not S2O 31 mol S2O 32 times 158. 1 G nut S2O 31 mol not S2O 3 equals 1. 68 G. Mass of nut S2O3 required to yield 0. 110 m S2O 32. 0. 11 mol S2O 32 1. 0 L times 1 mol S2O 32 1 mol not S2O 3 times 158. 1 G nut S2O 31 mol not S2O 3 equals 0. 17 G. 15 1. The mass of nut S2O3 required to dissolve 1 G of Ag Br in 1 L of water is thus 1. 68 G plus 017 G equals 185 G. Check your learning. AgCl S, silver chloride, has a very low solubility. AgCl, letter 1D460, Ag plus, letter 1D44E, letter 1D45E plus Cl minus, letter 1D44E, letter 1D45E. KSB equals 1/6 times. 1010. Adding ammonia significantly increases the solubility of AgCl because a complex ion is formed. Ag plus, letter 1D44E, letter 1D45E, plus 2 NH3, letter 1D44E, letter 1D45E Ag, NH3 2 plus, letter 1D44E, letter 1D45E. Kf equals 1. 7 times. 107. What mass of NH3 is required to prepare 1 L of solution that will dissolve 2 G of AgCl by formation of Ag NH3 2? Answer: 1 L of a solution prepared with 5 GNH3 dissolves 2 0 G of AgCl.